So, right side. Yeah, see. Is PDF or PowerPoint easier to do? Either one works. Share the screen. HDMI. HDMI's plugged in. Should be good. want to start right at 9.
Yeah, wait till 9.
It's been a rough Wednesday.
Yes.
You guys okay if I begin? A couple more minutes.
Yes, to start, yeah.
Okay, so I'm AJ, and I'm going to be talking a little bit about this paper modeling of bond formation between polymer filaments in the fused deposition modeling process. Essentially what they're doing here is they're looking at ABS plastic and the material extrusion process, and they're looking at how well these extruded filaments bond with each other and the parameters around that, and trying to optimize that. So what their big goal is in the upper left, material strength. From this research, they want to find ways to get stronger materials, and the way they're doing that is by improving the bonding between these filaments of ABS plastic. So this is sort of a flowchart on how they reach that goal of material strength. So what they want to maximize for getting the best bonding is a wetting between the lamina. So the lamina are the sheets of fused filament, and we want to get the best wetting. So it's 2 circles, and essentially want them to have the largest neck possible, because that's the largest surface area for bonds to form. And then we figure out how to maximize this through surface tension and adhesive bond measurements. And there's models already in place in previous literature that they examine, and they create their own heat transfer model and combine it with a sintering model to figure out what all these parameters are. And they're looking specifically at optimizing extrusion temperature and ambient temperature. So this is a diagram from their paper on the bonding between lamina. So the reason why, if I were to use injection molding to make a part out of ABS plastic, why it would be typically stronger than a 3D printed object is the void space. So if you're trying to build a part that has high strength requirements, then you want the voids in between the filaments to be as small as possible. To do that, you want the individual filaments to overlap as much as possible. So the heat transfer model they used, so the reason why they have a heat transfer model in the first place is such that they can model how the bonding is going to occur, and this is sort of a step towards that adhesive modeling, so they can figure out how the neck length is going to change and how much these filaments are going to overlap. So they had a fairly basic heat transfer model. They used the lump capacitance method. Some key features are that they assumed that the temperature was constant across the different cross sections. They had an elliptical cross section, and they assumed constant properties with respect to temperature, although they have another model for sintering where they change that assumption. So a comparison to other models throughout literature, the top line you see is a lump capacitance model, And the bottom dotted lines are from a 2D model from previous research. So the dotted models were using a square cross section, but they had better experimental data to model the properties. The lumped capacitance method starts at a higher temperature and it cools down at about the same rate, but they compared this to experimental data and has figured out that for the purpose of what they're doing, the lumped capacitance method would be the best. So the net growth and wetting, in order to maximize the amount of bonding, you want to start, so this is using the upper left-hand diagram. To maximize the amount of bonding, you want the net growth. You'll see it's labeled 2y in figure 4, diagram 2. You want the most net growth and diffuse as much as possible, and then after that you get the randomization of the bonds, which actually contributes to the strength. It's really hard to measure and model the randomization of the bonds, so they're basing all these calculations on the neck length for the different filaments. So on the bottom left, figure 5, this is actual experimental data they have. So this was a sintering experiment, meaning that they got 2 small pieces of extruded ABS plastic. They had them next to each other and they put it in a isothermal environment. I believe these were, it was 200, 220, 240, and 260 degrees Celsius. This is for the 200 degrees Celsius, and they're looking at the bonding as a function of time. And it gives a more realistic view of what's happening in figure 4. So the net growth mostly occurs above 200 degrees Celsius. They found that any net growth is negligible once the material is cooled below 200. And yeah, here's experimental data from the sintering experiments. So the goal of these sintering experiments were to figure out the relationship between surface tension and the actual thermal conditions that you're creating. So what they did is, as they heated these, they measured the net growth as a ratio of the radius of each of the filaments. And they're able to use the function in the lower right-hand corner to model the surface tension with respect to time. The gamma is the surface tension in units, I believe, newtons per square meter. And then the theta is a trigonometric expression of the ratio of the net growth versus the radius of the filament. So the experimental data here was isothermal. So what they're able to determine is that at the higher temperatures, you're getting the higher dimensionless neck radii. So this supports their claim that at higher temperatures, you can get better neck growth and better bonding. They did another experiment with sintering. So this was ramped sintering. So they had the same types of particles, cylindrical extruded particles of ABS plastic, except this time it was ramped from 200 degrees for 10 minutes at different rates. So they tested at 5 degrees Celsius per minute, 10 and 15 degrees Celsius per minute. So they were able to determine here the dependence of temperature on the surface tension. So they were able to actually determine that as the filaments get hotter, there's actually a negative correlation to the surface tension. So as the filament got hotter, there was a negative value for each interval degrees Celsius that you're going up, that the surface tension is going to decrease. So they conclude that there's potentially an optima that you could reach in terms of temperature with extrusion temperature. So these two graphs are different effects of temperatures that you have control over when you're doing an additive manufacturing process with material extrusion, specifically ABS plastic. On the left is the effect of the envelope temperature, so the ambient temperature of the 3D printer. And on the right-hand side is the extrusion temperature. And what they noted is, so the difference between the dotted line and the dark straight lines are relatively consistent changes in temperature. So the ratio of 260 degrees to 280 degrees is equivalent in terms of normalized ranges in which you typically use for these processes. So they raise it a certain relative amount, and they determine the effect of the dimensionless neck growth. And they were able to determine that in figure 8, the dotted line is much higher than the straight line, showing that the neck growth is higher, and the extrusion temperature has a greater effect on the neck growth. You see two sets of lines on figure 8. The second set of lines that are sloping downwards is the cooling process for the filament. And another note that they made is even though you get better performance at higher temperatures will eventually start degrading the bonds between the ABS plastic. Again, adding to the need to find experimental data to optimize the extrusion temperature for the maximum strength in your parts. Another factor that was tested was the heat transfer coefficient. So they determined that heat transfer coefficient has a very high effect on the dimensionless neck radius. So in order to maximize the strength between your parts, you actually want a lower convection coefficient. And the downside to this model is that there's no experimental data to back it up. This was done entirely with the lump capacitance method, so take this with a grain of salt. So just to summarize, they went through the heat model. They figured out what their best heat model would be for their system. And that was the elliptical surface, or the elliptical cross sections with the lump capacitance method. And although like this model worked for them, it's not experimental, and there's always better models like take other things into account, like the changing properties. Like one thing that you might think of is as the filaments are bonded together in the areas where the neck growth occurs, there's a density change because you're compressing the plastic, and that was not taken into consideration. Also, when the necking forms, there's bond randomization between the two filaments, and that was not really modeled with this approach. And it was also mentioned in the literature that there is also bond formation that occurs below 200 degrees Celsius, yet above the glass transition temperature. It was assumed to be negligible, but they mentioned that other studies have found that this could be contributing effect to the total bond strength of the process. And then also only consider 2 pieces of filament being bonded together at a time. So not multiple layers where you might have one filament going into a certain, so you can imagine like you already have filament lie down and you're lying this on top, and it might stick to one strand of filament but not the other, so that could contribute to material weakness as well. Any questions? you see how it says top of filament and filament center line? Those are completely overlapped.
Do the 2D models make the same assumptions as the capacity model? Like you had some assumptions listed in the slide previous for
Yeah.
the constant temperature. Does the 2D model have the same assumptions as that?
No, the 2D model is mostly based off of they solve the entire differential equation. So while the top model, the low capacitance method, is that per unit cross section, the temperature is completely the same. The cross section temperature is different. That's why it gives the different lines of top filament, filament center line, and the filament interface between the build plate because of the different cross sectional assumption. And they also took into account the changing density as a function of temperature. But and one thing that was noted in the paper is that the model didn't consider changes of density with respect to the interface in which the filaments are being fused.
I would say this model is surprisingly bad.
Yeah. What was strange is that I understood it fairly well on my very first try, and if it's that simple, then I really had some doubts about the accuracy of it.
I said a question about the model of this neck growth, and it takes a long time for these necks to happen.
Yeah.
Especially if you look at the one like the time lapse videos.
Yeah.
Right. So really for complete removal, the neck takes around 840 seconds, which is quite a bit of time. And you don't actually see this in the fused deposition modeling system. They don't hold the part, or a thermal material extrusion process. They don't hold the part at elevated temperatures of 200 C for 840 seconds. So I think it's interesting from a kind of a scientific point of view in terms of understanding how these necks would grow in time. I don't know if this is the most practical model because this wouldn't give you too much insight into how a part actually densifies. Right? That'd be a long time to hold it. And most, at least not that I'm aware of, they don't usually heat treat these parts once they're manufactured. It's like pops on the printer and it's ready to go, right? Maybe there's someone who's heat treating them. Then you have to deal with slumping and all these other issues that could potentially happen. This is a long time to hold the part at pretty elevated temperatures, especially for polymers. I imagine that locally, a lot of this stack form very quickly because it's coming in at fairly elevated temperature, but it's not there for very long.
I was also curious about how they actually did the experiment because if it was just two pieces of filament sitting next to each other, then it'd just be them naturally sort of flowing into each other rather than there being some sort of pressure applied to it.
To force it together, yeah. And then my other question is on slide 9. So they go through, I guess on the following slide too, they've had all these different convective heat transfer coefficients, right?
Yeah.
Where did these come from? Because they're kind of random. It's like 50, 100, or 25, around 25 watts per meters squared Kelvin difference. Are these kind of randomly selected, or are there any physical basis for where these came from?
There wasn't much information about the convective heat coefficients besides that this came entirely from the lumped capacitance method, or the lumped capacitance model. And figure 11 is a little bit different because it does include some of the experimental sensing data, so it was able to match the temperature with the dimensionalized net growth radius, or ratio, not radius.
I know that at the beginning of the paper they were talking about some of the bulk material properties for parts that are produced
Yeah.
using this method. And then you were mentioning that they later went in and were talking about there's an optimum between they, say that there would be any work being done, or they know of any work being done about how that would affect the material properties of the actual part being produced, other than net growth?
They talk almost exclusively about net growth, although they do mention that sort of the trade-off of getting to a higher temperature and getting a better net growth, which supposedly has a huge impact on strength, is that you might be able, at a certain temperature, the bonds are going to start to degrade, and then I believe, so whenever I use my 3D printer and I set it too high, if it's too hot, then you run into a lot of other issues like curling of the plastic, and I believe a lot of those sort of heuristics haven't really been taken into account.
So, but the FDLs, like you can choose the kind of fill, right? You can choose like a honeycomb or like a solid fill, or like depending on fill type. How do you think those will like affect these like things? Because the fill pattern is gonna be the clearance between each fill.
So I think they're looking on a smaller scale, although if they were, I believe there would be a very big difference if you're like printing a solid part, so that now if I have the filament come in, I have more surfaces to bond to and a higher surface area to form these bonds and have the bond diffusion occur. So they did not examine the
Saying on all
support
sides, those are just two filaments next to each other.
Mhm.
So it's almost like a solid fill, right? Like scale up.
Well, see a microscopic view of a solid fill.
Yeah.
Questions? All right, thanks, Adrian.
Yep. You want to keep this presentation?
That's right, we have it recorded, so.
Okay.
Okay, so this is where we left off on Tuesday. We were looking at, I guess take a slight recap. We looked at a few different cases where we're looking at an impulse of heat energy. And we're saying a laser acts like a direct delta function or an impulse. And we said, well, we know that this is not 100% true, so let's start to add a little bit more complexity in here. Let's look at the case where the laser is now modeled and the laser energy is distributed. Okay. So by that, we mean going back to some of the models we talked about for, say, laser power. Oops. All right, this would be, terrible. This would be one of the models that we looked at. Here we had simpler ones than this, but this is one that's showing it 3D, and so this is the taking into account that one, the laser energy has been measured or has been observed to be Gaussian in the XY direction, and then also that when the laser energy is an incident on a powder bed, you have scattering. This is from reflection, so you have some internal scattering, which basically propagates the laser energy deeper into the powder bed, and then you also have scattering that ends up as a reflection in terms of not 100% coupling of the laser energy into the powder bed. It just reflected back into the environment and heats up something else besides the powder bed, right? Heats up the walls of the chamber. So we're looking at how do we take this information about the heat source and build this into some of the things that we've been doing already, right? And so this looks like the case of the thick plate. The thick plate simulation that we were doing earlier, but instead of a direct delta function for our laser, we were looking at laser energy that's distributed. Okay. And so this is adding a little bit of complexity to the problem. We're going to see how this affects things. If you look at the homework assignment that we do that's due next Friday, it has problems with distributed energy. Right? How do we solve that? So this is, let me erase my notes from. I don't know why it's not going away. So this goes back to how do we solve non-homogeneous PDEs. So a reminder, non-homogeneous PDEs, we have this forcing function. Thus far, we've looked at forcing functions of the form of direct delta functions, and we did some things to get rid of this time variable to make it purely in the form of space. But just to note, when we had non-homogeneous forcing functions, we had methods to solve this, right? So this is all based off of, everything we're doing is based off Green's function. So if we have a Green's function that solves the solution for the direct delta function, and we have non-zero initial conditions, and also we have the form of this non-homogeneous term, we can solve ux of t by using the Green's function with convolution. So this is just adding kind of elements to this Green function for diffusion equation with infinite boundary conditions, or in the case of the one we're talking about, this is the half plane where we have a even reflection about z is equal to 0. But you have some sort of Green's function that defines the response of the system to a direct delta function. And then we are looking at convolutions in space here. So this is looking at the convolution for the initial conditions, psi or phi y, and convolutions in space of, sorry, so a lot of lines going on here. That won't go away for some reason. Convolutions in space of the Green's function with now our non-homogeneous term, and then a convolution in time. And we're not going to get to convolutions in time in this class because we're, at least for this part of the class, because we're going to look at this moving frame that always follows a laser spot that gets rid of time for us. So we saw this with the Rosenthal equation. But this is the basic method that we're going to use. This is a 1D. We now have to turn this into an equation for this 3D case here. Right. So any questions on this idea? This is kind of going back to module 2 a little bit. Okay. All right. So this is the 1D solution. The equivalent expression for this in 3D is basically the same idea, but it's just a little more complicated because now we have to consider x, y, z, as opposed to this example it just had x with integrating factor y. So these become now vector valued. Okay, so we have a Green's function that is a function of this vector x. Just to note, this vector x in 3 dimensions would often be variables x, y, z. We have our integrating factor x primed, and then we're doing this integration in space for the homogeneous solution and the non-homogeneous solution as well. So this would be the general equation for how do we use Green's functions to solve the non-homogeneous partial differential equations in 3 dimensions here.
All right, any questions on that idea?
I'll show an example in a second.
Okay, so this next part, this isn't really an example, this is just working things out. So the statement is pose the moving distributed heat source problem as a convolution solution. And we're going to go through this. So to note, this is coming from material we've already gone through before. We know that the Green's function for the basically say the Rosenthal equation or diffusion in space when you have a moving frame of reference is if we have S of x vector, right? Just to make sure this is on your notes on this page. This will be slightly different than I had before, just that we have a change in coordinates from x to zeta. So S of x vector to pi zeta squared plus y squared plus z squared